lots of money to be made there. And it makes me angry because you just don't have control over it. They take your money and they may make you money, they may lose you money, but they take their money.
I have a question.
Yeah.
Do you know who normally teaches chemistry / physics 412, physical chemistry, thermodynamics?
It's been Ken at least the last couple years.
Brokerage had a lot of game theory in it.
I can't go any further with that because I decided that was not what I was interested in.
What, game theory?
No, in buying and trading stock.
Oh, I see.
Okay, we're going to talk about quantum mechanics today. Particle in a box will be the only problem we're going to look at. So we're going to look at quantum mechanics very specific to that problem, particle in the box problem. Quantum mechanics, when you actually start a quantum mechanics class, one of the very first things you learn is the Schrodinger equation. So this equation right here is the Schrodinger equation. That's an A. And despite me having taken German, the pronunciation of Schrodinger still bedevils me because the O umlaut kills me. So I know that Anne is taking German. How would you pronounce this gentleman's name?
Schrodinger? No. Schrodinger?
See, I'm not going to argue. I've had some teachers that say Schrodinger, and you hear all over the road. We just can't agree because apparently our knowledge of the German language does not allow us to understand umlauts. So, Erwin Schrodinger came up with this equation, and what it is an energy balance equation. Now you look at that and you're really unlikely to say, oh yeah, totally energy. What this is p squared over 2m plus v. What is p squared over 2m? Everybody's learned this in this class. P squared over 2m. It's an equation. Momentum squared divided by 2 mass. Maybe it would help you if I said that's equal to m squared v squared over 2m. Cancel one of those m's. 1/2 mv squared. Okay, so that's kinetic energy. And what is v? That is a higher physics level of saying potential energy. So the right side, the right side of this equation is kinetic energy plus potential energy. What's with that? This character here is a capital psi, as opposed to this here being a lowercase psi. So that's a capital psi. Why is it that I said p squared over 2m when I have this funky thing? Well, it turns out, remember I told you that in quantum mechanics that wave function has all of the information. But you have to find a way of getting the information out of it. And we get the information out of it by using what we call operators. Operators are functions that act on another function. And so the operator for momentum is equal to I h bar actually I think it's minus I h bar ddx. That's the operator for momentum. So if I want momentum squared over 2m, actually we put a little thing over here, usually you say that's an operator. So the operator for momentum squared over 2m, that's just going to be minus I h bar squared times ddx acting on ddx all over 2m. What's minus squared? Positive. What's I squared? Negative. So h bar squared is, of course, h bar squared, so that gives us the minus h bar squared. ddx of ddx, that's just the definition of the second derivative. And then we have the over 2m.
Are those partial derivatives?
Those are indeed partial derivatives. I know my handwriting can be bad. It wasn't supposed to be that bad that you couldn't tell the difference. They're partial derivatives, absolutely. So our wave function can have variables besides x, and this is technically the momentum in the x operator if I do the d dx. I have to use the del operator if I'm doing the total. So there I did momentum in the x direction squared. So this is an operator. When the operator acts on the wave function, it gets you the value times the wave function. So if I have my p operator acting on that wave function psi, that gives me my px value times psi. So that's why we put the little carré, or hat, as we like to say in physics, over the operator, because an equation like that seems redundant at best if you don't.
So what are we? We're starting with Schrodinger's equation.
Yeah.
For what?
What we're going to try to do is find the solution for the energies and positions for a particle if it's in an enclosed box. But we have to have some background if we're going to start doing that. And so we have the Schrodinger equation, but if we're going to work with it, we kind of need to know what the equation is. And so this here is just to try to lay out where it comes from and what's going on in quantum mechanics. And this operator idea, operator acting on the wave function, gives me the value times the wave function, is really important for quantum mechanics. Otherwise, you just have this function, you don't know what to do with it. So how we get information out of the wave function is by having operators that act on the wave function. So the kinetic energy operator is that. And so if I have that kinetic energy operator acting on my wave function, which is what I have right here, the kinetic energy operator, acting on the wave function, then that's going to give me the kinetic energy value times the wave function when I actually do the math. Now over here, I just had V. That's also an operator. One's an operator, right? One acting on a function gives me that same function with the value of 1. So this function, the potential energy operator here, is just whatever the value is of the potential energy. Now you can also have potential energy that depends on position. You would have to put in the operator for the position dependence there. But in today's work, our potential energy operator is just going to be its value. What about this side? It turns out that the energy operator is I h bar d dt. And so the energy operator acting on psi is going to give me the energy multiplied by psi. Psi being the wave function. So this is the equation that Erwin Schrodinger came up with as a wave, well, it's a wave equation. From it you find the wave function. You find the solution to this equation, and that's your wave function that gives you all the properties of your particle or wave, depending on which way you want to talk about it. So do you understand what the Schrodinger equation is?
Wait, so you said it gives you the wave function, or it gives you the information from the wave function?
It's what you use to find the wave function. So that's its purpose. The purpose of the Schrodinger equation is to find your wave function. You just have to put in whatever your potential energy operator is, and then you solve the equation. Where does it come from? This side here was energy. Forgot to put the plus side there. It comes from an energy balance. The total energy is your kinetic energy plus your potential energy. It's a pretty simple origin. Of course, coming up with it isn't as simple as having the equation saying, look, its total energy is kinetic energy plus potential energy. But that's what this equation is at its root. So it's just using an energy balance to allow you to find your wave function by finding the solutions to that. Now, the particle in a box, also called an infinite well, is a situation where you have a particle that can only be inside the box. It can't be outside. So in physics, how do we describe it can only be inside? We say the potential energy outside of the box is infinite. How do you move a particle from inside the box to outside if it has a potential energy of infinite outside? You don't. Or you could have given me the annoying answer that's true but not possible. You just use an infinite amount of energy to lift it out. Right? You don't, because you can't access that infinite amount of energy. So that's how we say this is in a box, because we just made it, so there's an infinite amount of energy to get out, you can't get out. Inside, we'll just say potential energy is 0, because it makes our calculations easier. Remember, potential energy is simply based on your chosen reference. Why not choose your reference to make it 0? Okay, so let's go forward. This Schrodinger equation is time dependent. As you will find if you take a quantum mechanics class, we usually work with the time independent Schrodinger equation, and then the question comes, well, how do you get the time independent Schrodinger equation? Well, if we take and we say, let's suppose that I can separate my time portion from my spatial portion in my wave function. This is not always possible. It depends on the form of your potential energy function. So you actually have to pay attention to what is my potential energy function to determine if this is possible. We're not going to do that. We're just going to say we're dealing with a case where it is. So if I say, notice capital psi is my overall wave function, lowercase psi is just going to be the spatial portion. This always bedevils me because I tend to just gloss over the difference in capital and lowercase, and then I get confused. So if that's the case, then I can just put that in. So E times psi of x phi of t equals I h bar d Let's start with that.
That's a capital, right?
This is a lowercase psi. Is that what you're asking?
Is it?
Yes. In everything I'm writing here, it's lower cases. How do you know the difference? You know the difference by the leading edge. If the leading edge has a curve on it, that's my lowercase psi. If it's coming straight down, it's going to be my capital psi. So if I look at this equation, first of all, how does the function that's a function of x, psi, depend on time? This is a trivial question. It doesn't. So that means I can take that right out of the derivative because it's a constant in terms of time. If this was not a partial, I couldn't do that. If it was an exact derivative, I'd have to worry about how x changes with time. But since it's a partial, I just bring that out, and that's going to be psi of x I h bar d phi dt. Well, now I have a psi here. I'm going to change colors, actually. Now I have a psi here and a psi here that there's no function acting on them. They're just multiplied by psi. So what I'm going to do is, because you can't technically divide it out, we will in just a moment. You can't technically divide it out because there are going to be positions where psi is 0. And if you divide it out at those places where psi is 0, you just broke the math rules. But we can factor that out. I can say this is psi of x times e minus I h bar d phi dt equals 0. Right, so I subtracted the right-hand side to the left hand, and then I factored out the psi. What conditions make this true? Either psi of x equals 0 or e equals I forgot to put the psi here. That's a mistake. Right, there is a psi, or a phi. There's a phi right there that I forgot to put in. or E phi equals I h bar d phi dt. Now, since psi of x is not generally equal to 0, then the lower equation is going to have to be generally equal to 0 everywhere except for the very specific place where psi of x is 0. Since it's a function of time, that means that the lower case has to be true. So I was able to get essentially the same as dividing out the psi's by factoring it out. It's just this is mathematically pure. So what do you do to solve a function like this? I have this function. How do I find that solution? This is something we can and have done. First, I have to
Is that E of E phi?
E times phi is equal to I h bar d phi dt.
Or do we want to know what the
We want to know what phi is.
integrate?
Before I integrate, I have to do something.
Move the E, maybe, or the P, or something. Move something.
I have to start with an S.
Substantiate.
It's been too long since we had our first lecture of first semester, clearly.
Set our limits.
You got the first two letters right. S-E.
Supplement. Oh, SE?
Not T, but S-E.
Separate.
Separate. Separate what? The variables. Excellent. We got there. So we have to separate the variables. What are our variables in this equation? And T. Phi and T. So we need to separate them. How are we going to separate them?
Multiply both sides by dt.
Okay. I have to multiply both sides by dt and divide by phi. So I'll multiply both sides by dt and divide by phi, and I will have E dt. Now, I change that to an exact, to a proper. Why is that legal?
What? Oh.
That's right. Because it's the only variable involved, it's appropriate to change from proper to an exact. Or, excuse me, from a partial to an exact derivative. Because there's no other variables, they mean the same thing if there's no other variables.
On that side, you're saying there's no.
No, in this equation. In this equation, there are no other variables besides phi and t. Hence, it's exactly the same meaning if you have a partial or an
Oh, I see what you're saying.
exact. Okay, now we do what you've been saying. What is that?
Supplement.
Supplement? Like that.
Okay, no. We integrate both sides. This side only depends on time. This side only depends on phi. And so we just integrate the two sides. And I'm going to do these integrals without limits. Can you believe that in physics class? I know it seems wrong. What do we get for the integral of the left side? That was tough. What do we get on the right side?
I h bar
We're going to have a long ln somewhere, I think, right?
d phi with respect to. Oh, I get it.
Okay, I'm trying to solve this for phi, so what should I do next?
Well, divide by I H bar and then E the things.
So I now am left with... What's 1 over I equal to? We don't like to leave i's in denominators. It's what?
Oh, 1 over I. 1 over the square root of
I to the
I
negative.
mean, the negative 1. Should be I the negative first. Yeah, what do you say?
Okay, let's
Oh,
think this through logically.
yeah. No, wait.
No, before logic comes in, Chad has something to say.
It's negative I.
It's negative I is correct. I to the first power is I. I to the second power, you told us, was minus 1. I to the third power is obviously I to the second power times I, so that's going to be minus I. And I to the fourth power is plus 1. Okay, so if we have 1 over I, if we multiply top and bottom by I, we'd have I over I squared. I squared was minus 1, so it's I over minus 1 minus I. So this is minus I e t over h bar. Now the step that you were saying to get rid of the natural log,
Raise everything, we'll have e to the things.
e raised to this is equal to e raised to that. But e raised to the natural log, those are inverse functions, and that gives us phi is equal to e to the minus et over h bar. So there is our time dependence equation.
Where did I go?
The I, it's right here. It's just hard to see when I forget to write it.
I never thought I'd ask that question. Where did I go?
See, I was going to try to be funny as a psychologist. You know, the id said okay, you have the ego and the superego. The ego is more of the I, and the superego is the. So I was going to blame it on the id. We have found the time solution, the temporal solution to the Schrodinger equation, if we have a constant energy situation. Now we're going to come back to that time-dependent Schrodinger equation and look at the other portion. If I combine this with this, right, because there's an equal and an equal. So first I set the first two equal, now I'm going to set the first and the third equal, since they're all equal. You guys are acting like that's inappropriate. Like I'm being a bad man by suggesting this. So I'm going to rewrite this. We have E capital psi.
Well, what are we looking for now?
Now we're going to look for an equation that only depends on position, but not on time. As long as v is only a function of x, what we're doing is appropriate. Okay, made a mistake on the last one. Remember I said if it has the curve, it's the lowercase. It needs to be uppercase here. Now we'll substitute for psi. So we'll have e lowercase psi that t looked too much like an x for me. Okay, so there I've substituted with our psi that's just the linear combination of the position psi and the time phi. Well, what do you notice here? How does the derivative with respect to x affect the phi function?
It's a constant.
It's a constant, so it doesn't. And so what I can do is now I'm going to do the bad math. I'm just going to divide everything by why is this bad math? Because technically there's going to be a time when that function is 0, and at that time I broke the rules. But you saw from my work before, I could have rearranged, factored it out, and said, okay, except for these times, and it still comes out to be legitimate. And so we have our time-independent Schrodinger equation. And we want to find solutions to this bad boy. How do you suppose you'd find the solution to this? Even though I pick up at this point in the next slide, I'm going to continue here before we get to the next slide. What would you do if you were going to try to solve this for psi?
No. Yeah. Factor out
Yeah.
Factor out what?
psi from the right side.
Or maybe move the E over and then factor out, well, move that whole thing over from the left onto the right and then factor out side.
Okay, because we have a derivative here, we can't actually do that. But what we will do is separate the derivative from everything that's not the derivative. So I'm going to solve this for the derivative. D second psi dx squared is equal to, well, I have to multiply everything by 2m over h bar, right? H bar squared. And then I'm going to have, if I move this over, it's going to change signs, but I had that minus sign, so it's going to be a plus. And then I have this one here that was a plus, but because of that minus sign, it's going to change signs. And so here is a second order differential equation. Now I said for our purposes for today, v of x will equal a constant. So the right hand side is a constant times psi. I forgot the times psi. Times psi. The left hand side, well, it's a second order differential equation. Who knows how to solve this? Wow, me! Because I've taught differential equations, I'd better know. Here's what we do for a class of your nature. We tell you the solution. The solution is psi is equal to e to the bx. Now let's check and see if this is true. Right? Because I just told you it's the solution. You don't know differential equations, but you know calculus. If psi is e to the bx, what do I need to do with that to check to see if my equation is true?
The derivative?
Yeah, take the second derivative. This is one of the easiest things to take a derivative of. What is d psi dx equal to?
B.
That was not tough. In fact, I could also write that as just b times psi, couldn't I? It says e to bx is psi.
B, Preto?
What is b? B is a constant. We don't know. It's a constant. Part of what we're going to do is find what b is.
Oh.
So if the first derivative is b of psi is b psi, what's the second derivative of psi going to be?
B squared psi?
Yeah, you guys are some smart little cookies there. So it's b squared psi, and from my equation, that should be equal to 2m over h bar squared times, and I'm just going to put v because I said our v is constant, minus e psi. Okay? If this stuff's a constant, and this is a constant, is this a correct solution?
Yes.
Yeah. And in fact, we can say then that b squared is equal to 2m over h bar squared times v minus e. Everybody good with that? All righty. Keeping this in mind, let's go to the next slide. Slide 4 of 12. We've already seen these two equations. We worked out where they come from. We already worked out the solution to both of them, haven't we?
Yes.
Yeah, this one here we had yes, CC, senor. Captain. Okay, so we had that solution. This solution here we had where b squared was equal to that. So we've seen the equations, we've found the solutions. Now we're ready to apply it to an actual situation. And we are choosing the easiest problem you can do pretty much in quantum mechanics.
Why is that not as comforting?
Eulers Equation. You guys know Eulers Equation? It's actually very cool. It's e to the I phi is equal to cosine of phi plus I sine of phi. We use this a fair amount in physics. So our solution for the time portion we could have written as a combination of cosine and sine. Now you notice you have an imaginary value there, and usually that causes us a little consternation. But this is not the value for energy, it's the value for our wave function. Our wave function can be complex. It's just our observables, things like energy, position, those have to be real. We can't have an imaginary energy and an imaginary position. Unless you're Calvin from Calvin and Hobbes. Yeah. I don't know if you guys have seen Calvin talking about complex variables, but it's reasonably funny. What's a complex number? You mean something like 13-y, 14-y? Yeah. Or like when Richard was 6 years old and showing off to his siblings that he could count to 100. I got up to 99. And then I went to Tindy because I did not know what number came after 99. Story of my life. I get to the very last step, improving my knowledge. I run out of knowledge. Okay, so we're going to find the stationary states, the solutions to the time-independent Schrodinger equation for the particle in the box. We've already seen our solution. I hope I remember to put b squared the last time I wrote this. Alrighty, let's take a crack at this. We have three regions because we have potential V is different. So I'll name this region 1, region 2, and region 3. So I have V1 is equal to infinity, V2 is equal to 0, and V3 is equal to infinity again. So let's just look at our solutions. In region 1, V is equal to infinity. Therefore, B squared is equal to 2m over h bar squared times infinity minus e. Approximately what value would you assign to this? Infinity, right. It's infinity multiplied by constant, so I'm just going to put it's approximately infinity because infinity is not a specific number. Which means that psi 1 of x is equal to e to the... forgot one thing. This gives me b values. It gives me two b values. What are the two values for b? They're what? Positive and negative infinity. So I'm just going to put plus and minus infinity here to save some time. So I'll have psi 1 is equal to, I'll put a plus sign, e to the infinity x, or psi 2 with a minus sign is equal to e to the minus infinity x.
What, psi 2 or psi 1?
It should be psi 1, thank you. I fixed it. So I have two solutions. Well, how do I find my full-on solution if I have two solutions?
Eliminate the impossible?
Well, we're going to do that, but there's a step before I eliminate the impossible, believe it or not. The true solution is going to be taking the linear combination of these two. So my true solution is going to be psi 1 is equal to some constant times psi 1 plus some other constant times psi 1 minus. And go ahead.
I was confused about where did this come from?
Because we have two solutions. Both of them are solutions to the equation, so the actual solution is just a combination of the two. So, it might be 5 times psi 1 plus 3 times psi 2, or 5 times psi 1 plus 3 times psi 1 minus.
Will both of those be 0?
Well, when we get to the end, yes. We haven't gotten there yet. So this would be equal to a e to the infinity x plus b e to the minus infinity x. Now, what are the values for x in the region of psi 1? What are the values for x? They're negative. So this is x is less than 0. Now, if x is less than 0, then a e to the infinity x is a e to the minus infinity. What's e to the minus infinity? 0. So, because x is less than 0, this solution here is 0. What about e to the minus infinity x if x is negative? E to the infinity, which is infinite. So this goes to infinity. But a rule is that my wave function has to be finite. So if my wave function is finite and e to the minus infinity x is infinite, what does b have to be? That's right. Now that's a reasonable amount of work to get to the answer that Chad told us. What does that say? Psi 1 is equal to a times 0 plus 0 times infinity. And this is a case where this is an exact 0. That's an approaching infinity, so the exact 0 wins. And it's equal to 0. Yeah. This actually makes sense. We've done a lot of math. And the math is just that. It's math. When I was taking math classes, I could do the math like crazy. It didn't mean a lot to me. So let's go back to meaning. One of the things we can get from this is the probability of a particle being at x within a region dx. And we learned from class, we talked about just yesterday, that's going to be the psi of x mod squared times dx. Well, what is the probability of my particle being outside of the box? 0. So this side should be 0. Well, it turns out that psi pretty much has to be 0 for that to be 0. And so I could have started just being logical and saying psi has to be 0 outside the box because the probability of being outside the box is 0. Right? I could have started with that. But that's putting the solution before the problem. We do need to make sure our math bears that out. And so we did the math first, and the math said psi was 0, and then we said, okay, and logic also said psi had to be 0. Well, that's a good result. I mean, that's peachy keen, really. So we've just found that psi 1 of x equals 0. Using all of that now hard-won mathematical knowledge, what can you tell me about psi 2 or psi 3? Yeah, I'm also going to have psi 3 of x is equal to 0. I could have gone through all of the math. Again, it would have been the same, essentially, except for now I would have had x is greater than L, so x is positive, and I would have had A is the one that had to be 0, and B could have been anything but, or no, except I said it the other way around. Last time it was B that had, I don't know. They would have been zeros. So we're left with just figuring out what's going on in region 2. Region 2 is where the particle is, it can exist. So let's look at region 2. And I'm going to have to make a new slide here to do my work in region 2. So in region 2, I have psi in region 2 is equal to e to the bx. And I have b squared is equal to 2m over h bar squared times v minus e. But what is v? V is 0. So that's equal to minus 2me over h bar squared. Just like before, to get b, I have to square root it, right? And when I square root, I get two answers, one that's a plus and one that's a minus. So I'm going to get two answers for b. And what is it?
1 over h bar square root 2 MEI.
That's what I was hoping to hear. I'm actually going to leave the h bar. I was trying to decide if I should put it in the square root or not. Okay, so I have plus or minus I, because square root of minus 1 is I. And then I have square root of 2me over h bar squared. So let's make an abbreviation. Let us say that k is equal to the square root of 2me over h bar squared. So I can just say this is plus or minus ik. It's just shorter to write it that way. And so now my solution has two solutions. Solution plus equals e to the ikx. Solution minus is equal to e to the minus ikx. And so what is my full solution going to be?
The addition of them with the A's and B's.
Okay, it's a linear combination. A linear combination of these two. Now, before I do the linear combination, why not? Let's do the linear combination first and then I'll do it. I can't decide.
Now, do those constants have to be the same as they were in the situations?
No, they're different constants. I moved past that. Usually we actually say A, B, C, D, E, F. And so it would be C, D. Here, I will do C and D just so. On my next slide, I actually have A and B. But C and D, so it's unique. Psi plus e to the ikx. Eulers formula. Euler's formula allows me to rewrite this in terms of sine and cosine. Sometimes it's more convenient to have it in sine and cosine. Sometimes it's more convenient to leave it in the exponential form. If you put it in the sine and cosines, you know what's real and imaginary. Sometimes that's useful. Sometimes not. So this would be cosine of kx plus I sine of kx. Almost fit it in.
Wait, where? Oh, right. Because
I wrote Euler's formula before.
Right.
I'm going to move this stuff over so I have room to...
Euler's formula is e to the ix is equal to that?
It's e to the I phi is equal to cosine phi plus I sine phi.
Okay. And phi is, we're saying phi is kx in this case?
That is correct. And so this is going to be cosine of kx plus I sine of kx. And this one here is going to be, notice cosine of plus kx and cosine of minus kx are exactly the same thing. So it's still going to be cosine of kx. Sine of minus kx is minus sine of plus kx. So I have to change the sign here. And so when I add these together, if I have C times psi 2 plus D times psi 2 minus, they both have a cosine kx, and I'm going to have C plus D cosine of kx plus I, and then it'll be C minus D because of the minus sign in the psi 2 minus, sine of kx. So that's my complete solution.
Why is it C minus D?
Because I had psi plus had a plus sign here, and psi minus had a minus sign here. And so since I put D with the psi minus, I have a minus sign in front of the D.
I get what you're doing. Yeah, okay.
So let's go to my next prepared slide. My next prepared slide shows the solutions that we've just found. Notice I used Euler's formula there, got it written out. And here's where I said A and B for my two constants. And so I have that solution. Now we apply the boundary conditions. We are nearly done, which is good because we are 4 minutes from being out of class time. Boundary conditions. There are usually two boundary conditions, but for the case of an infinite barrier, which doesn't occur in real life, one of those boundary conditions disappears and we only have one boundary condition. And that boundary condition is that my wave function has to be continuous. You can't have the wave function as 0, 0, 0, 0, 5. It has to go from 0 to 5. Right? Can't have a discontinuous jump. So I have two boundaries. Boundary 1. X equals 0 is my first boundary. And so I'm going to have psi in region 1 of 0 is equal to psi in region 2, 0. Right? Because I have, that's the boundary between wave function 1 and wave function 2. And it has to be continuous, it has to have the same value. Then I just plug in my values. What was psi in region 1 at position 0? 0. 0 equals, what about psi in region 2 at 0? It'll have to be 0, but I have an equation for it. I'm going to stick with the A and B since I have them written on this page. So that would be A plus B cosine of 0 plus I times A minus B sine of 0. What is sine of 0? Boom. What's cosine of 0? So what does this equation tell us? It says 0 is equal to A plus B. Therefore, A equals minus B. And I can write this as then psi of 2 is equal to 2IA sine of kx.
Oh.
Because if I substitute for B, for minus B, I put in A, that's A plus A. So that's 2A. And we have that I there. Okay, I'm good with that. That's at boundary 1. Now let's go to boundary 2. X is equal to L. I'm going to have psi in region 2 of L is equal to psi in region 3 of L. Well, psi in region 2 of L, just put what I had from above. 2IA sine of KL is equal to, what's psi in region 3? 0. Well, there are two ways to make this true. What's the first way? Make what? Actually, not KL0. Let's start with the other one first, though. The other one is what we call the trivial solution. If I set A equal to 0, then I have psi in region 2 is 0, which means the probability of the particle existing in the box is... That's really not a physical answer if we have a particle in a box. So we throw this answer away. We call it the trivial solution. It's the solution that says, no, there really isn't a particle in a box. And so we go with the other one, which is the one Tori started with. I just wanted to get that out of the way, Tori, instead of doing the whole long problem and then say, oh, and there's a second solution we throw out. So the second solution is sine of KL equals 0. And Tori identified already that gives us KL equals 0, but there's other solutions. What's another angle that makes sine equal to 0? Okay, pi, because we're going to do it in radians here. Or 2 pi or 3 pi, etc. So we have KL is equal to an integer multiplied by pi. Now what if KL is equal to 0? What do we have for our answer? We have 0. So we actually have to throw this one away as well because it's also trivial. So it's only going to be integers of pi, so n is equal to 1, 2, 3, etc. Only positive integers are allowed here. Okay, now that we have that, let's see what that tells me. What was k?
It was the square root of
2me over h bar squared,
yeah,
probably.
that was just
So, I forgot the L. Let me put the L right there. This is my condition. What is it going to tell me? It's going to tell me there are only certain energies possible because the n's have only certain values possible. So if I solve this for E, I'm going to have to square both sides and then move stuff across, and I will have E equals pi squared n squared over L squared. If I divide by this stuff that was in the square root after I've squared, I'm going to have an h bar squared on top and a 2me on the bottom.
Not the e though, right?
Yes, not the e because that's what I solved for. Thank you, friends. Keeping me from making big boo-boos. So we have now quantized energies. There's only certain energies the particle can have if it's in the box. Only the energies allowed by this. So our solutions have... This here has A instead of L. Let me just change that to an L. And put psi here instead of E. Our solutions, notice this has square root 2 over A. And we had I2 capital A. What's the difference? The difference is one more condition that your wave function has to be normalized. We don't have time to talk about what normalized means, but it actually sets what that A value is. And so it turns out that you have the front part square root 2 over A in your wave function.
is
And you have-
L in every case here.
Yes, A is L in every case. And since we had that condition on K's, we just made the substitution, so we have n pi over L.
And what is L? L is just the boundary.
L was the width of the box, as shown in this picture. So we have the wave functions now as shown. If I want to find the probability for the particle's position, how do I find it? We square psi, and then we multiply by dx, of course. So if we square psi like this here, it would become
Multiply by what you said?
by dx. It'd be something like that. That's my best rendering when I'm out of time. Where is the particle most likely to be found?
At the peaks.
At any one of these peaks. So it has 4 probable positions. What's the probability? What's the average of those positions? Halfway. What's the probability of it being halfway if it's in that state? 0, because the square came to 0 at that point. So the most likely position, right? The red there was squaring the wave function, and 0 squared was 0, so it was 0 for the probability at that position. Its average position, if you take a bunch of measurements, will be in the center, but the chance of it actually being there is 0. You'll never find a measurement there. Depending on which state it's in, you have different positions. I know you got to go. I just want to make sure we got to this. This is the payoff. You have only certain energies allowed. Some positions are not allowed. The positions are more likely.
Can we just not open the box and say it's everywhere?
So the
So
values
now I'm Schrodinger's
you
cat.
said it's not allowed to be in,
What was that?
like the values at the
The-
bottom.
Places where this is 0, it's not
Yeah.
allowed to be.
And then it is allowed to be everywhere else.
Yes, and it's more likely to be at the tops of those because those are probabilities.
Why did you make it bigger?
Because I was squaring it.
Why did you square it?
Because probability is psi mod squared dx. And so that's why.
And before you just had them like, well, why were the graphs smaller?
Because the graphs were just psi.
Oh, okay, that's what you just. That's the lowercase.
Yes, that's the lowercase.
And then in the box here in the slide, it's uppercase, right?
No, that's lowercase as well.
What?
I said for my handwriting.
I know, but it looks like, okay, yeah. I
That
see it.
if it's printed, the capital psi looks like this. Oops. Let's make that one a lot more reasonable.
Looks,
It looks more like that for the printed form.
okay.